Hello all. In this session, we will start the module 4, that in the moment of inertia. In the module 4, we have two chapters, that is centroid and moment of inertia. Please watch the centroid because without centroid you can't understand the moment of inertia. So please do watch centroid chapter. Okay, what is moment of inertia? It is defined as the algebraic sum of product of area and the square of distance from the particular axis, and that is denoted by Ixx or Iyy. So while doing the centroid, I have told while measuring the y-axis, you are measuring while measuring the x-axis, you are measuring from y. If you are measuring y-axis, you are measuring from x. So same way here also, there in the centroid we are denoted. The centroid is denoted by x bar and y bar. Okay, a centroid is denoted by x bar and y bar, right? But here the moment of inertia is denoted by Ixx and Iyy. So this one you need to remember. It is given by I is equal to AH square. Actually, centroid, while doing the derivation, I have said that each and every forces are actually a area, right? Each and every forces which is acting on a plane, we are considering as in a small area. That small area into distance we are considering. But in the moment of inertia, same that area into distance square we are considering. But here I have taken h, no an h, no problem, but we are taking twice the distance. Here we are taking twice the distance. Okay, I'll tell you why. And the unit of moment of inertia is mm to the power of 4. So here we are taking unit of the moment is mm to the power of 4 because it is area into h square. It is a second moment of area which is measure of resistance to bending and forms basic to strength of material. Okay, so this is very much important while constructing, to measure the resistance of bending to forms basic strength of material. Mass mi is the resistance to rotation and forms basic to dynamics to rigid bodies. Okay, here you can see the figure. You can see the figure here. So it is in a 3D shape. So here you can see this is a small area. So which is measured from, as I told, from y it is x, from x it is y. So that's the thing. And next the formula is Ix is equal to inner integration of y square into dA, and Iy is equal to integration of x square into dA. So this is the thing. Y, see this, y distance from x axis to the area dA, and x is a distance from the y axis to the area. So as I said, once again I'll just explain the definition of the moment of inertia. Moment of inertia is a term used to describe the capacity of a cross section to resist bending. So the cross sectional area we are increasing in the structure, maybe in a beam or a column, pillars, whatever, we are increasing the cross sectional area to resist the bending. Okay, after the application of the load there will be a bending in the structures. So we are resisting with the help of moment of inertia. It is always considered with respect to reference axis such as xx or yy, that is xx or yy, xx or yy. So it will be like this, xx or yy. It is a mathematical property of a section concerned with the surface area and how that area is distributed about the reference axis. The reference axis is usually a centroidal axis. That's why I said before solving moment of inertia derivations or a problem, please go check the centroid problems and derivations, because moment of inertia is a continuity of the centroid problem. Okay, after finding the centroid of centroid problem, we are taking one reference, we are taking one reference axis, we are taking one reference axis in the problem. After that we are continuing to do the moment of inertia problems actually. So that's why, so please go watch the centroid problems first. Okay, the moment of inertia is also known as second moment of area, and it's expressed mathematically as Ix is equal to integration of ay square into dA, and Iy is equal to integration of x square into dA. So as I said, in the centroid we are taking only, one minute, in the centroid only we are taking area into the distance, right? But in the moment of inertia we are increasing the cross section, so we are taking double the distance, that is twice the distance. So that's why it is called as second moment of the area. A centroid is also known as first moment of the area, so this is second moment of the area. Okay, here you can see in the figure uh, mass concentrated around spin axis. Here you can see when you're spinning, you can see the mass will be concentrated around the the spin axis. Easier to drill needs less force. If you are taking the drill, the broom handle or any bar, when you're holding vertically, you want less force to rotate. If you're holding horizontally, you need more force to rotate this. So that is the example. And moment, already we know that moment or a torque or moment of a force is a tendency of a force to rotate an object about an axis. For example, one more example I can give. Just take a stone or a ball, just tie it with a rope or a thread, and just rotating. So what will happen, or rotating, you can see as the area increases, there will be a different force. As the area, very small area, if you're rotating, the force is different. So that is a difference you can find out. Okay, here also you can see one more example, that is understanding the moment of inertia. So in the first one, the girl rotating about an axis passing through her center of mass, and the second one, uh, the boy and is rotating about an axis which is not passing through her center of mass. So in the first figure she is rotating herself, and the second figure she is taking others help. So which in this case the rotation is easier and there is a less resistance against the angular acceleration. So if you see that, so that first one is the easier to rotation and less resistance against angular acceleration. So in the case one, you need a less the rotation compared to the second one. Okay, here also one more example I have taken. First figure and second figure, you can see if the weights are very less distance, it is different to the that weights are in the keeping the weights in a different distance. So easier rotation will be first figure. You can see easier rotation will be first figure compared to the second one. Okay, next the topic is radius of gyration. Radius of gyration of an area with respect to a particular axis is the square root of the quotation content of the moment of inertia divided by the area. It is a distance at which the entire area must be assumed to concentrate in order to product of the area and the square of the distance between them. And that means, for example, in the inertia, Ix is equal to k square into a, Iy is equal to ky square into a. So here we are taking radius of gyration as a indicated by k. So for if you're taking k, if you are want to solve x-axis, we are mentioning as a kx, and if you are solving in the y-axis, we are taking as a ky. And the most effective column section to resist buckling is a circular pipe, because it has its area distributed as far away as possible from the center. So that's why radius of gyration will be useful. Okay, so the radius of gyration is distance k away from the axis that all the area can be concentrated to result in the same moment of inertia that I have already told. That is, if you're taking solving in x-axis, kx is the root of inertia in the x-axis, actually inertia in the x-axis divided by a. So similarly for the ky is equal to root of iy, that is inertia y divided by area. Okay, a very important topic, that is parallel axis theorem, important for both internals and exams. Okay, in the figure I have taken very the simple area, and I have marked the distance of centroid. Here, see this, if you are taking a small area, so I'm marking a centroid. This is dy from the x and dx from the y. So like this, I'll just tell the definition or a statement for this. The moment of inertia of an area with respect to an given axis is equal to the moment of inertia with respect to the centroidal axis plus the product of the area and the square of the distance between the two axes. Actually, this one we are going to prove in the next slide. The parallel axis theorem is used to determine the moment of inertia for composite sections. Um, so here, to solve the problem of moment of inertia, we are just using the parallel axis theorem's formula. So that is the purpose of solving parallel axis theorem. Okay, here you can see Ix is equal to integration of y plus dy whole square into dA. Here in the definition you can see the moment of inertia of an area with respect to a given axis is equal to the moment of inertia with respect to centroidal axis plus product of the area. See, here you can see plus product of the area and area of this square distance between the two axes. So the same thing, the equation, the equation we have taken, just a second. Yes, same thing, the definition we have taken here. And if you integrate that integration, if you do the integration, so y dash square plus 2 into, that is they solved in a square plus b square into 2ab, so the same formula. So at last what is going to happen, so this will be a 0, we consider as in 0. So finally we are getting integration of ix is equal to ix bar plus 0 plus, because this will be going to cancel, so that's why it is 0, plus dy square into a. So similarly, if you're taking for iy, so see, you can observe for iy is equal to iy bar, that means integration in the centroid in the y-axis plus dx square into a. So this one we need to remember, that is for ix dy square will be there, for iy dx square will be there. Okay, so this is it, and after this we are going to solve a problem on this. Thank you.